Hello, and welcome to another video on machine learning and biotechnology. My name is Ian Hoffecker, and this video is going to be about training neural networks and some of the practical issues that may arise when you're doing that. So if we look back to some of the code from the last video, last exercise, we use this TensorFlow Keras package to build this neural network that could solve the XOR logic gate, a capability that the logistic regression cannot do. And we kind of set you loose and did not explain too much about the architecture or the parameters that we used. We just showed that if we added a single hidden layer here with 3 nodes or 20 nodes and trained this neural network, that we could get good performance out of it. But where do these numbers come from? How many layers should we have? How many nodes should we have? And what are some of the pitfalls that might arise when we're working with larger data sets with more variables? That is some of what we're going to cover now. So if we recall back to the training process, so it was working by this process of backpropagation, where the idea was that we would use the chain rule from calculus to be able to compute the gradient for any given weight in our network. And we would do this for all the weights, and we would use these products of various derivatives that each of which individually was calculatable. And even though the final results that we're interested in, the change in the loss function with respect to a particular weight, was itself did not have a direct formula that we could use, but by combining these other quantities, we could get this. And so this was the process of training the network. And one of the things that we noticed, first of all, is just how many, the sheer number of parameters that we have. And so this is going to be a kind of general feature of these models, that there are a lot of parameters and that the landscape of the loss function or of the parameter space is going to be complex. So if we look at a simple line fit, right, that's a 2-parameter fit, and these linear models have a convex landscape. So at any point in the parameter space, the loss function has a smooth gradient that can be computed locally, and which is going to give us a compass direction that leads us to the global minimum. And that means that we basically know where we're going at any point in time. Whereas with these nonlinear models, with neural networks, with a lot of parameters, our loss landscape is going to look something more like this. Maybe it's going to have a lot of pits and valleys. And if we imagine we're a blind walker on this surface with the parameters in our directions of movement are defined by parameter axes, and our elevation is defined by the value of the loss function. If we imagine being a blind walker on this space, it's going to be very hard for us to know if we're in a global minimum, where we should go if we happen to be trapped in a local minimum. And as a result of this, a lot of the techniques that we're going to be employing are heuristic or kind of rules of thumb rather than a perfect deterministic formula for achieving the global minimum. So what are some of these pitfalls that we can run into? So the main one that is going to come up, or one of the main ones, is, of course, overfitting. So we probably have a kind of an intuitive grasp of overfitting, where let's say we have some training data, the blue dots here, and we have some test data. So here we're considering something like a linear regression, right? And we're fitting a line to the training data. And unfortunately, the training data is not perfectly representative of the test data. So if we train our model on this, and especially if we were to, say, extrapolate, try to guess the y value given an x value in this upper range here, we're going to be quite far off from where we would want to be if we had knowledge of the test data. And the problem here, of course, is that there's noise in the data. So when we have a limited training data set, we are potentially subject to that noise in a way that causes us to fit our model to features of that noise rather than the general trend that we're trying to find. We can also look at a kind of classification example. So this is for function fitting, but we can imagine a case where, say, we have two inputs here, we have two classes here, the blue and the magenta. And the idea here is that we want to distinguish these two classes and create a boundary between them. And overfitting would be something like this, where we've drawn a line around every point that is perfectly capable of perfectly accurate in terms of this training data set. But we can imagine that if we were to refresh this, look at some test data, maybe they're not going to fall perfectly along this contour here. Instead, we're maybe going to expect some noise at the boundary. And actually, our model is going to perform worse than maybe if we just had a straight line going through here, or a curved line with not quite as many features as we have here. So that's kind of the intuitive perspective here for overfitting. But can we be a bit more rigorous about this in our definition? And so one way we can think about overfitting is in terms of comparing the loss function for our training data and some validation data. And so this can be done during training through data partitioning. So we already know about train test data partitioning, where we split our data into some data that's for training and then some that's meant for evaluating it after it's been trained. But we can also, during the training, set aside another subset, a subset of data that is designed specifically to evaluate how the training is going on each epoch. And if we do that, we can get a curve like this, where we're seeing the training loss and the validation loss. And while the training loss function is going down, as we would, of course, want it to be doing, so we're trying to optimize it, trying to minimize the negative log likelihood, for example, we have a problem here, which is that the validation loss is, first of all, diverging from the training loss, but more worryingly, it's actually going up at this point. So the loss function hit its minimum on epoch 24 here, and actually began to get worse, began to rise afterwards. So you could imagine that maybe if you're just looking at the training data loss function, you have a false impression that your model is getting better and better and better after epoch 24, but in fact, it's actually getting worse. And so one of the easiest fixes for this is to implement something called early stopping. So this is one of the first tools in the toolbox. And the idea is that we're going to set some thresholds. So we're only going to allow this validation loss function to go up a certain amount. And if it hits that amount, we're sure that it's probably not just noise at that point, that what we're looking at is the beginnings of overfitting. Then we're going to halt the training altogether and revert back to the historical best value for the validation loss. So we will go back to this minimum here. And then that would be the set of parameters that we use for our model at the end, and not the final set that we settled upon in the training data, which would correspond to an overfit model. So that's a very simple solution. Another thing we can do, so that requires you to sacrifice some of your data. So once again, this is a data partitioning approach. And of course, if you're partitioning your data, you're getting less and less access to it. You're using up more and more of it for things other than training. So that can be one downside of this technique. And another thing to consider is we can also get some intuition or get some idea of what the loss function is doing based on its values. So even if we don't have validation data set aside, and even if we're not tracking it, what we can do is pay attention to a key benchmark, which is this value here, 0.693. So why is this important? So we have, at least for the sigmoid activation function, we have this loss function, right? The negative log likelihood, which is this binary cross entropy. And so this is for the sigmoid, and the sigmoid, right, is this function that's going to transform a linear combination of features into a probability. It's going to map this value from 0 to 1. And if you're at 0.5, this corresponds to a point where you have equal likelihood to be class 1 or class 0, to be type A or type B. And 0.5, so if we take the negative log of 0.5, so if we compute this loss function for 0.5 here, this has the value 0.693, or minus log of 1 minus 0.5 is also 0.693. So this corresponds to a loss function value for a model that's performing equivalent to a random guess, a 50-50 guess. So we're looking for performance that's better than this. So we want to see a loss function value that's lower than 0.693. So why is this important for overfitting? Well, if we see a loss function value that's much below this number, we might start to become suspicious of overfitting. So if we're looking at loss function values of, say 10 to the minus 7, then we are a bit suspicious. So this corresponds to a model that's almost perfect, perfectly predicting the result. And while this might sometimes be the case, so it of course depends on the situation, but in a lot of cases, we're probably not looking at perfect predictions. And so we can start to get suspicious at that point. So paying attention to this benchmark can be a useful tool as well. So that's overfitting, recognizing the signs of it. But what can we do about it? How can we avoid overfitting? So early stopping was, one approach. So another thing we can do is something called regularization. And the idea behind regularization is that we're going to penalize complexity in our loss function. And so specifically, what we're going to do is, so we have our regular loss function, right? The negative log likelihood for our maximum likelihood estimation approach, but we're going to add another term here, which is proportional to the weights in our model, or proportional to our parameters. And then I haven't written this here, but this is usually scaled by some factor. So lambda here is some scale factor that is going to determine the strength of this penalty. So why is this a penalty? So we have these weights here. So the idea is essentially that if we want to crank up any of these parameters, we have to spend loss function points to do it, right? So we're trying to minimize the loss function. So by increasing the values of any of the parameters we have, we're also hurting, increasing the loss function, or making our score worse for that particular configuration. And so only if we get a corresponding payback in terms of the binary cross entropy in this case, do we feel that we are justified in spending those points or increasing those parameter values. So if we go back to this line fitting example, we could fit this line here with this very steep slope. And of course, the slope, right, is one of the weights here. So that's weight 1 here is the slope of this line. And a penalty might encourage us to use a shallower value, a lower value for the slope here. And so we would thus be less likely to fit an extreme value when we see it here. And in some cases, this means we're going to get better fits or more conservative fits to our training data. So why might this be effective? So a kind of intuition for this is that we're trying to influence the result as much as possible using as little as possible. And so this has the result of selecting features. So feature selection is an important task that we have to do. So in most data sets, some variables are going to contribute more or less to prediction. They're going to be more or less linked to the outcome that we're trying to predict. And so what we want to do is identify those features. And so maybe we have, say, 10,000 parameters, 10,000 variables, inputs, and we have 10,000 weights looking at each of those variables, but maybe only 10 of them are actually needed to very strongly predict the result or outcome variable. And if we're penalizing weights, then we're going to be setting most of those variables to 0 and rewarding those that actually do lead to predictions. as opposed to a more liberal model, which would allow you to spend points wherever you want. And then maybe you would amplify a lot of features that are not actually contributing to the prediction. So it has the effect of simplifying your model and kind of zeroing in on those features that are the most important. And in general, this tends to be good, especially if you have noisy data with a lot of variation that's not predictive of your outcome variable. So is regularization, so this is regularization. Should you ever not do this, or is there any reason not to do regularization? So in fact, there is a kind of trade-off. So regularization, if we think of it as this kind of lazy model where you're only spending points, lazy or frugal model, we could say you're only spending points, only upping the values of your weights if it's absolutely beneficial. So one of the kind of consequences that you can have is if your model is quite sensitive to, so if you have, say, sharp minima in your model that are hard to detect when you're not close to that minimum in the loss landscape in the parameter space, then you're going to have a hard time reaching that, because in order to reach that point, you have to sort of spend parameter value points. You have to put value into your parameters in order to explore that space in the first place. So if your space is hard to explore because it's got sharp valleys that you don't have much indication of their existence, if you're far away from them, then you're going to have a hard time convincing the model, so to speak, to go there in the first place. So regularization has the tendency to, if it's too strong, lead to underfitting of a model. And maybe you have features that do require extreme values of the parameters, but you haven't found those because it's hard to reach them in the first place. So basically, broad basins or so-called flat minima tend to be more conducive to discovery if you have regularization turned on. Another strategy for regularization, so that's one approach. Another way you can do regularization or avoid overfitting, in other words, is using something called dropout layers. And the idea here is that we're going to turn off certain neurons or turn off certain nodes in our network randomly. So the key parameter here is the fraction of neurons or nodes that you're going to drop out each iteration. And you're going to shuffle this or change this every time so that you give different combinations of nodes an equal chance to contribute to the prediction. So this allows you to prevent monopolization of, say, maybe one neuron has, due to the random initialization, kind of sensitivity to the initial conditions of your model, the initial parameter values that you chose, you might have zeroed in on one or two neurons that are kind of hogging up all the predictive power. But it may turn out that other neurons have an important contribution to prediction as well that only become clear when you've turned off these monopoly neurons. And so in general, this also helps you generalize and reduce overfitting. And it has the advantage that it's computationally cheap, right? Just turning off neurons. One of the disadvantages is that it can make networks harder to optimize sometimes. So you may have structures that require the interactions of groups of, say, 3 neurons. If you are always turning off one of those, then you may have a harder time detecting or catching those interactions. And then finally, another way that we can avoid overfitting is to use different sampling strategies from our training data. So if we go back to this loss function that we have, so the goal, of course, is to minimize it. To do that, we're fetching the gradient. So this is, again, the direction of this steepest descent that we need to navigate our parameter space. And we have this update rule, which says that once we have the gradient, this list of slopes or derivatives, we're going to multiply it with a step value or a learning rate. And that's going to allow us to change the old parameters into the new ones in each update. But we can fetch this gradient in multiple ways. So one way to do it is with a full batch. So we can compute the average gradient for all the data points. So if it's gene expression profiles and we have 1,000 individuals as our training data set, then we could compute an average gradient over all 1,000 individuals for each of these weights and each of these parameters here. And that would give us a very smooth, potentially very reliable value that's going to point towards a minimum, but it has the disadvantage that, first of all, it's computationally expensive to use your whole training data set for each gradient update. But also you have the disadvantage that this will give you the tendency to memorize the data. So any peculiarities, features, noise that are present in your particular training data set are going to contribute strongly to the gradient that you compute if you're using the full batch. And so to remedy this, another approach is to use what's called stochastic gradient descent. And the idea here is that you're just using a single point, so in a single individual, to compute the gradient each time. And so instead of this very smooth, kind of reliable gradient that you're computing from the average of all data points, you have this much noisier, much more erratic gradient that's computed each time. But this noise can sometimes be advantageous, can help you jump out of local minima. So it's a bit less prone to a very fixed path towards a single point. And that single point can sometimes be a local minimum that you would get stuck in. Whereas a stochastic gradient descent, you're kind of shaking your way across the landscape, and you do have this possibility to sometimes hop out of local minima that you're stuck in. But of course, it also has the advantage of being very noisy. So kind of middle ground between the two is mini batch gradient descent. And the idea here is that you're computing the average gradient over a mini batch of, say, 10 or 20 individuals instead of one, or instead of the full batch. And so again, this is to combat overfitting. So if you're using the full batch, you can memorize the data. You have a model that is potentially memorizing the data or overfitting to any structure in the data that might not be due to the underlying patterns, but simply due to noise that's present in your particular data set. And then it's also computationally inefficient. Stochastic and mini batch are going to give you this faster computational complexity and this ability to potentially escape local minima and not get overfit as much. So that's overfitting. And what other kind of knobs and tools do we have to tweak these models? So one of the things that we've covered before is learning rate, and or in other words, the step size. So we have this update, right, that's happening every time we compute the gradient. We multiply that with our learning rate or step size in order to create an update to all the parameters. And the size that we're using here is very important for determining the approach to our minimum. And so if we look at this chart here, so this is a chart of a loss function with, on the horizontal axis here, the learning rate. So we have smaller learning rates, smaller step sizes towards the bottom, and larger step sizes towards the top. And if we look towards the left here, this is kind of the zone of underfitting. So we're not getting the best, or in other words, the lowest values of the loss function at these low learning rates because it's so slow. So the approach is very slow. And we have kind of a sweet spot here, so a good learning rate. And this, of course, is going to change depending on your model. So this sometimes takes a bit of trial and error to determine where you ought to be. And then you also have this exploding region here of large step sizes where the model is not performing well, basically because you're overshooting the optimum. So if we imagine a lost landscape here, we're taking steps that, rather than settling into this basin, are just kind of bouncing back and forth here, unable to really land where they ought to. So most of the learning rate scheduling programs where you have an adaptive learning rate or a changing learning rate involve some sort of decay where you have larger steps towards the beginning in order to cover some ground and not take too long. But then you slow down and take smaller and smaller steps in order to kind of finally settle into whatever basin you've found in the end. But there's more exotic things as well. So if we look at, say, warm-up, as it's called, the idea here is that you actually start with a really slow learning rate and then ramp up to a larger step. and then again taper off towards the end. And the purpose of something like this is to deal with unstable values that you might have for the gradient at the initial step. So when you've initialized your parameters, you have all these random values, and computing the gradient involves propagating or multiplying these signals many times. This can sometimes lead to exploding gradients, infinite value or close to zero, vanishing gradients, just numerical instabilities that if you do a little bit of settling or a little bit of optimization at a slow learning rate, you can sometimes smooth out these problems and then ramp up or have a larger step once these things have kind of stabilized. Another tool in the toolbox is what's called standardization and normalization. And the idea here is that we want to vary our input features from 0 to 1. So this is normalization. And the reason you want to do this is to put them all on an equal footing. So we want kind of convergence to solution. This requires computing these multivariable gradients. And if we imagine, say, one variable tends to vary on order of magnitude of, say, 10 to the 15, and we have another variable that's varying on the order of 10 to the minus 6, this is going to create numerical problems where if we're kind of comparing or computing numbers on these hugely different scales, we're going to have, say, rounding errors maybe that just come from the computer, rounding digits off that may have a huge impact. So this is sort of a numerical stability issue, and we want basically all the variables to be treated more or less equally, and that way the model is going to pay attention to features according to their relative differences and not on this absolute scale that we might be putting them on. And this is also good for regularization. So if we're using these regularization techniques, these will also be more effective if we've standardized or normalized the data. And so there are two types here. So normalization down here is when you scale the data from 0 to 1. So we squash it in this range from 0 to 1. So it has this formula here to transform your data. And then standardization is when you transform the data to have a mean centered at 0 and a variance of 1. And so unlike normalization where you have a hard boundary, in standardization, you don't necessarily have a hard boundary at 1 and minus 1. You can have outliers that go beyond that, but the idea is to have things kind of roughly varying on the same scale. So when to use which, this can be a bit of an art, but in general, if you have symmetric data, then this is going to be better for standardization, so kind of Gaussian-like data. Whereas if you have very skewed data, then normalization would be the more natural choice. Okay, and then finally, how many layers, how many nodes should we add? What effect does this have on the performance of our networks? And so depth, that's the number of layers. This is what enables a network to learn complex features. So if we remember back to the XOR logic gate, we saw that it could not be predicted with a simple logistic regression. And a logistic regression, if we recall, is very similar to a single layer neural network or a single layer perceptron. And the main difference between logistic regression and, say, multi-layer perceptron was that we're adding this additional layer, this hidden layer. And this allows us to have hierarchical representation of abstract features that are not directly represented in the data, but instead are represented by, say, interactions between variables in that data. So we think of it as kind of a placeholder or a sort of memory for higher order relationships between your variables or hierarchical learning. So the more tiers of this hierarchy, the more kind of layers of abstraction that you need to understand the data, the more layers or more depth you're going to need to achieve that representation. And so if we go back to the XOR logic gate and we made this spreadsheet neural network, right, where we looked at the inputs to the logic gate 0, 1, 1, 0, and we use the neural network with this sigmoidal activation function at the end, and saw that, yes, we could get the XOR logic, which is detecting whether input variables are different or not. So it's blue here if they're different, it's red if they're not. If we remember, the way we got this working was by adding this hidden layer with 2 nodes. And each of these nodes also had a sigmoid activation function that we could look at. And we didn't really analyze the results of these intermediate nodes here. But something interesting that we can notice now is that actually these correspond to intermediate logic gates. So the first one, H1 here, corresponds to an AND gate. So you have 2 inputs, A and B, and the output is a 1 if and only if A and B are both 1s. And so we can see that here we get the blue, the higher value for the case when both inputs are 1s, and it's a lower value in all other cases. And conversely, over here we have H2, the other node, which has 2 inputs again, coming from X1 and X2 here, which are 1 or true in all cases except for the double negative case here. And we see that is the case. So when both X1 and X2 are 0, we get the lowest value here for the activation function. If one were to rig an XOR gate with an AND and an OR logic plus an additional NOT gate, and so we have this kind of implicitly here with the -1 weight, which is penalizing the output of the AND gate here. This is what's going to give us actually the XOR logic. So a combination of an AND or a NOT gate represented hierarchically like this is going to give you this XOR gate. So this is kind of to reiterate this point that the depth here in the layer is allowing us to capture additional levels of abstraction. And the XOR gate is kind of a higher order gate that's based on these lower level AND and OR gates, which can be represented with linear models, but putting them together requires this additional complexity. So that's depth. How about breadth? So how many nodes do you need in each layer? And so the simple rule here is that we need more depth or more nodes in order to deal with more diversity. So if the problem is simple, there's not a huge level, many levels of abstraction or hierarchy in the data, but nevertheless, you have many different, say, contributions to the prediction. If we have 100 variables and all of them contribute slightly to the final result, then we're going to need more nodes to deal with those and each of their respective contributions. And in both the case of depth and breadth, we have to consider that we're increasing computational costs by adding more layers or adding more nodes. And we're also increasing our risk of overfitting by adding more parameters. So we can compute these numbers of parameters in either case with these formulas here. And in general, we want the simplest model that we can get away with that allows us to predict with the best performance. And so the exercise today was to look at some more kind of artificial gene expression data. And in this data, we have a case where there's 16 genes and they're grouped into logical groupings of 6 genes, and random truth tables or random logic gates have been generated for each grouping of 6. So actually there are 8,008 possible groupings of 6 genes out of 16 possible genes. So this is the number of kind of abstract or hidden layer features that we're kind of thinking about having to model. And the task here is to deal with 3 underperforming neural networks that have been set up, but are each performing poorly or as well as logistic regression in a case where we're expecting the structure and the data to be represented by a neural network better than what you would achieve with a logistic regression. So we're looking for a receiver operating characteristic that gets us above this orange line here. So that was the exercise. And so to kind of summarize here, we have all these tools in the toolbox. This is for training neural networks, which again is this non-convex problem that we're never really going to have a perfect solution to. And instead, we have all these heuristics where it becomes a bit of an art, sometimes requires perhaps some trial and error to kind of tweak these networks and really tune them until we can get them performing. And this sometimes takes a lot of, just trial and error and kind of experimentation sometimes to find out what is working well. But we can use these tools and use things like, tracking validation loss to get a better idea of what is actually happening when we're training these models. So that's it for this video. Thank you, and I'll see you again for the next one.